Okay, in this video we're going to look at projections. We've got a force F, 15 newtons, so they give us the magnitude, and it's 35 degrees from the x-axis. So I'm just going to draw the force F in here, something like that. 15 newtons and 35 degrees. Great. What we want to do is we want to break this into its components. So we're used to doing that along the x and the y-axis, but this is off of two other vectors and they give us these directions. So the first one is F1, and they say that's 13 degrees from the x-axis. We don't have the magnitude for that. So I'm going to draw F1 in here. It's 13 degrees from the x-axis. Something like that, where this is 13 degrees. And we'll call that F1. The other component vector is F2, which is perpendicular to F1. So here's F1. I'm going to go 90 degrees out from that. And that's F2. Again, where this is 90. Right, now if that's 13 and that's 90, we could obviously figure out this angle if we need to. So as you can see, it's kind of like, if you tilted this, it's kind of like F1 is your new x-axis and F2 is your new y-axis, and we're building this F vector, which is 15 newtons, and basically saying how much of each of these two vectors are used to make up this resultant vector. And so to figure that out, we're going to use projections. And what we're going to do is we're going to project F onto each of these two vectors, and then use some algebra to figure out what the magnitude of each of these are. So all I'm going to do is I'm going to draw from my vector down to the projected vector and cause a right angle there. So as you can see, that's created a right angle triangle here. And we're projecting F onto F1. Now the result of that is also going to be the magnitude of F1. In other words, how much of F1 is built into F. So that's going to look like this. F1, the magnitude of F1, is going to be equal to F projected onto F1. So we know the formula for that is F dot F1 over the magnitude of F1. And the problem is we don't actually know the magnitude of F1. In fact, that's actually what we're solving. So what we need to do is we need to take our other formula. We know the formula for the dot product. We can say A dot B is equal to the magnitude of A, magnitude of B, cos theta. So cos of the angle between them. So all I'm going to do is substitute this in for the dot product. And I know my angle is this angle here, which is the difference between 35 and 13. So that's 22 degrees. So I'm going to rewrite this and say F1 is equal to the magnitude of F times the magnitude of F1 cos 22 degrees all over the magnitude of F1. And the beauty of that is that now the magnitudes of F1 can go, and we can just say the magnitude of F1, the result of the projection, is the magnitude of F, which is 15, times cos of 22 degrees. So that's how much of F1 takes place in the vector F. Then we just need to do the exact same thing for F2. Now, as this projects down onto F2, it again causes a right angle, right? So you can think of F projecting down onto F2. We're going to have the exact same situation with the algebra happen, and all we need to figure out is what's this angle here, right? To figure out that angle, we can just say this is 35 all the way up to F, and well, in fact, we can break this 90 degrees down into the 22, and then whatever's left over. 90 minus 22 is 68 degrees. So this will end up being the exact same thing, where we can say the magnitude of F2 using the same algebra is just equal to the magnitude of F cos 68. 15 cos 68 degrees. And so that's the two components. F1 is built, oh, I missed a 1 here. F1 is built up of 15 cos 22, and F2 is 15 cos 68 degrees. So projections, draw the initial vector, and then create right angles down to the vectors, the component vectors that they're projecting onto. And then you can always substitute the dot product formula to be able to cancel your magnitudes.